We want to graph this polynomial function, p of x equals -2 times the quantity x plus 4 squared times x minus 1 times x minus 3. And we want to graph this without our graphing calculator. So we'll begin by analyzing the leading coefficient as well as the degree to figure out what the basic shape should be. And this is going to be the end behavior of the graph. So you can see we have a negative leading coefficient here, and because all of my x values here inside of the function, all of these would be 1x, 1 times x. My leading coefficient does remain negative. And then you'll notice that this particular function is actually already factored. It is in factored form. So one way to figure out the degree would be to actually distribute and expand this function, but that would be pretty tedious. So instead of doing that, we can figure out the degree by pretending like we were going to expand it. So for example, if we took this first quantity, x plus 4, the quantity squared, we know we would end up with an x squared when we did distribute. And then we would be multiplying by an x in my second factor, and then another x in my third factor. So x squared times x tells us ultimately we're going to end up with x to the 4th power. So we're going to end up with a degree of 4. Another way of thinking about the degree would be to just look at the individual degrees of the factors. So once again, we have a degree here. Whoops, sorry about that. We don't want to erase that degree. Okay, we have a degree of 2 for my first factor. Then my second factor, x minus 1, is a degree of 1. And my third factor of x minus 3 is also a degree of 1. So altogether, we see that we have a degree of 4. So it's a degree 4, and then it also has a negative leading coefficient. A negative leading coefficient. So since our degree is even, degree of 4 is even, and the leading coefficient is negative, that's telling us that the ends of my graph are going to point in the same direction, and because the leading coefficient is negative, they're going to point down. So you'll often see me do something like this where I make the inside of my graph dotted to imply that I don't really know what the inside of the graph looks like, but I do know that the ends are going to both point down. Now let's review how you actually would write that. This is called the end behavior of the graph. So we talk about what's the left behavior. So the left behavior of the graph would be as x approaches negative infinity. In other words, as we're traveling along the graph going left, what's happening to my y values? So it's like you're filling in the blank here. As x approaches negative infinity, what happens to y? Well, you'll see that your y values are going down, meaning they're going to negative infinity. So we would say that y approaches negative infinity as well. So the left behavior, another way of saying this, is that the left behavior of the graph, we say it falls. The left behavior of the graph is falling. Then the right behavior would be as x approaches positive infinity. So that's as you're moving along, going to the right, as x values are getting very, very large, what's happening to y. And the same is true. Y is falling. My y values are getting very, very negative, so y would approach negative infinity as well. So we could say that the right behavior is that the graph falls. So we try to encourage you to go ahead and use the more advanced notation, this arrow notation, rather than just saying that the left side falls and the right side falls as well. That'll just get you ready for your calculus courses. All right, so we've got our end behavior. So next, let's take a look at the x-intercepts of this function. So we know to find the x-intercepts for any function, we're going to let y equal 0. So in doing that, I'm going to put my work actually down here. I'm going to let y equal 0, so that would be 0 equals -2 times x plus 4 squared times x minus 1 times x minus 3. So we have this big polynomial equation to solve. Luckily, it's already factored, so this should be a fast one for us, because we know we're going to take each one of my factors and set them equal to 0. Now, you don't need to worry about -2. Even though -2 is a factor, it does not contain a variable. There's no x with that -2, so you're not going to get any additional solutions from the -2. So we have this factor of x plus 4. So if you set that equal to 0, you're going to get a solution of -4. x minus 1 is our factor. Set that equal to 0, and you have x equals 1. And x minus 3, when you set it equal to 0, you'll get x is equal to positive 3. So these are the solutions to our equation, and these then are the zeros of our function. Now, because all three of these values are real numbers, these become our x-intercepts. So I'm actually going to list them up here vertically. We have -4, +1, and +3 for the x-intercepts of this polynomial function. Because now we want to analyze what these x-intercepts, or excuse me, what's happening near these x-intercepts on the function. In other words, is the graph going to cross the x-axis, or is the graph going to just touch the x-axis at these 3 points, at these 3 x values? Well, let me go back down here to this answer that we got of -4, and let me rewrite this a different way for you. Remember, x minus 4 squared would be written out longhand as x plus 4 times x plus 4. So technically, when you set each of those factors equal to 0, you get this answer of -4 twice. You get it 2 times. And you could have also seen that from your exponent here of a 2. So we have a multiplicity here. So not only do we have an x-intercept of -4, but I'm also going to include next to it its multiplicity. So this is a multiplicity of 2. I'll just abbreviate that, a multiplicity of 2, because that answer appeared 2 times. Then looking at our next answer of x equals 1, that only appeared once, as well as x equals 3. So we don't have any multiplicities for the next 2 x-intercepts of 1 and 3. So now let's think about what that means about the graph. So because we have a multiplicity of 2, and because that is an even multiplicity, that tells us that our graph is going to touch the x-axis when x equals -4. We call it a touch or a bounce. Now at x equals 1 and x equals 3, those only appeared 1 time. The exponent was a 1 for both of those factors. And that tells us then that the graph will go ahead and cross through the x-axis at both x equals 1 and at x equals 3. So we have a touch, and then we have 2 crosses. All right, so the last piece then, there we go, would be to take a look at the y-intercept, and then we'll put everything together. So I always want you to have an accurate x-intercept as well as an accurate y-intercept. So to find the y-intercept, as always, for any function, we're going to let x equal 0. So that's basically like finding p of 0. We'll substitute 0 in place of x. And that's going to be -2 times the quantity 0 plus 4 squared times 0 minus 1 times 0 minus 3. And now we're going to go ahead and simplify. So we have -2 times 4 squared, which would be 16. 0 minus 1 will just give us a -1. And 0 minus 3 will give us a -3. So if we multiply all this out, what do we have? We've got a 32 times a -3. It looks like a -96. So our y-intercept is quite small, -96. All right, so now we're going to put everything together. So here's a summary of everything we've found so far, the end behavior, x-intercepts, and y-intercept. And this is actually the one time that I would be just okay with you graphing these on just a plain sheet of paper without graph paper, because I don't expect you to actually graph -96. I'll show you how I want you to do that. So we've got our x and y axis. We'll go ahead and include tick marks along the x-axis because we know our x-intercepts and we want to be able to plot those. And actually, now that I'm looking at this, let me adjust this a tad bit so I have a little bit more room. Let me go over here. All right, so we'll plot our x-intercepts. So we know that we have x-intercepts at -4, +1, and +3. And then we know the end behavior, we said that it was pointing down and down. So I'll just put in some arrows here, and I can adjust those later if necessary. Now we have a y-intercept of -96. So I'm actually going to let you just go ahead and put a tick mark down here that represents negative 96 and plot a point without actually including an accurate scale. That's okay. This time only. And now we want to actually put the puzzle together based on our X-intercepts up here and whether or not we're touching or crossing. So we said at -4 the graph was going to touch, so we would have to come from below, come up, and just touch the x-axis, and that means we're bouncing off of it. Then we know that we will have to also get my y-intercept here of -96. Then we would come up to +1, and we said the graph crosses, so we would just cross straight through the x-axis there. Then we'll have to turn around and cross back through the x-axis at +3, and then we have to end up pointing down. And if you need to kind of adjust those arrows, that would be fine to make those look a little bit better. So this is a rough sketch of what our polynomial function looks like. It has the correct end behavior, correct x-intercepts, and the correct y-intercept. Now, you might be wondering, how do I know, for example, this low point that I graphed down here, how do I know where that is? Could this graph actually go lower than that point, down way low here and then come up? And likewise, when I come up here for this high point, maybe it's not quite as high, maybe it's like that. How do you know your graph doesn't look like that? Or another option, maybe this graph comes up and doesn't go down quite as low, let's say, and maybe it comes up really high there. How do you know your graph doesn't look like that? And the answer is we actually don't know. We don't know how high up or how low down those points go. So one way to kind of get you a better idea would be to plot some additional points. So for example, you might take -1 and -2 and -3 and substitute them into the function to get y values. And likewise on the other side here, you might plot +2, substitute it, get the y value, so you know approximately some other points on the graph. Those are called mid-interval points. However, I don't require those of you. So there are several different ways you could graph it. What I'm looking for, though, are the correct shape and behavior, the correct x-intercepts, the correct y-intercept, and then making sure that your graph is touching in the right place or places and crossing in the right places. So, for example, what I have graphed here, all three of these graphs would be acceptable, the purple, the red, and the blue. We would have to dive a little deeper to get a better idea of exactly how low or how high the graph goes in these mid-interval sections. But this is good enough.